You have likely noticed that when you prompt an LLM, the words appear to flow out one by one. It feels organic, almost like it's thinking in real time. But there's a massive gap we need to bridge. You see, a large language model is at its heart a colossal mathematical function, a machine that performs billions of matrix multiplication every second. And functions don't speak English, they speak numbers. Language is fluid and continuous, but math is the opposite. It requires distinct countable units. To bridge this gap, we must break this smooth stream of text into pieces the machine can actually calculate. But where do we make the cuts? If we cut every character, the model sees the letter but misses the concept. It loses the big picture. If we cut by whole words, the vocabulary becomes an infinite, unmanageable list that no computer can store. We need the atoms of language. Subwords like trans and form, they are small enough to be flexible for any word, but large enough to keep the math efficient. We call these units tokens. This is the digital surgery that happens before the machine ever attempts to understand you, turning a messy human string into a clean numerical sequence. We need units that are small enough to be flexible but large enough to carry meaning. This is the art of tokenization. We call this algorithm byte pair encoding. It doesn't care about the rules of grammar, it only cares about frequency. It looks at a vast ocean of the text and asks which two units appear next to each other most often. Imagine we see the character E and R appearing together constantly. The algorithm doesn't know what they mean, but it sees the pattern. So it clicks them together into a new permanent block labeled ER. It's an iterative process. Once the machine merges E and R, it might notice that ER is frequently followed by N. It then merges those two, creating ERN. It keeps doing this until it reaches a target, say 50,000 unique patterns. This is why Apple might be one token while a complex word like bioluminescence is broken into fragments. The model can always fall back to those smaller pieces to understand words it has never seen before. This approach is unbreakable, whether it's a Python code, a medical journal, or a new slang term. The tokenizer just sees recurring patterns. It builds a vocabulary that is perfectly tuned to the data it was trained on. But how does your hardware perform this at speed? In a high performance system, we don't use slow string matching. We use a structure called Finite State Transducer. Think of it as a massive logical maze stored in your CPU's cache. As the computer reads your string, it walks this maze. Every character is a turn. It doesn't search a list, it follows a path. Now we have our list of token IDs, but these are just integers sitting in your system RAM. To actually think the model needs these IDs in the GPU, they are sent across the PCIe bus. Inside the GPU, these IDs acts as a coordinate. An ID tells the GPU to pull that row of the matrix. This is the transition from discrete to continuous. This is why LLM can be tricked, because the model only sees these chunks. It's often blind to the individual letters. If you ask it how many R's are there in strawberry, it might fail. To the AI, it's just two IDs, 452 and 891, whatever. The problem is that the GPU, the most important part of the machine, is also the most impatient. If the process of turning your text into tokens is even a few milliseconds slow, the massive processor is left sitting idle. It's starving for data, waiting for the surgery of tokenization to finish before it can actually start thinking. We optimize for cache locality and memory layout. Tokenization turns the messy, fluid nature of human language into the rigid, fast-moving reality of silicon. It is the first breath of every AI response. We have taken a string and turned it into silicon-ready vector. This is the moment language becomes mathematics and the machine takes over. Thanks for watching.